Good afternoon, colleagues. Good afternoon, participants. You are most welcome to day 2 of the Advanced Statistics and Experimental Designs. Is it day 2 today or 3? Today is day 3. So you are most welcome to day 2 of the experimental designs. And thank you for joining in on time. Thank you for joining in on time and always being with us here, making our trainings not to be in vain. We also thank the facilitators for always being here with us. So my name is Salmanda Pewangituamata, and I'm sure most of you have already seen me in the previous meetings. I work at the Reform Secretariat as a technical specialist, research and development. Today, we are continuing with our training on day 2 of the experimental design, and we really request you to make sure that you continue participating as you've been. Also, please, if you have been called to share the screen or to ask your questions, please always check your microphone so that you start sharing the screen right away, so that we do not waste a lot of time in trying to share the screen and all these in questions. Please, if you finished with what you are sharing or with your questions, please make sure that you mute your microphone to not cause a lot of distraction during the meeting. And most importantly, what has been always been asked by the facilitators, we tend to not listen to what the instructions that are being given to the facilitators, and you find that most questions are being raised over and over when they've already been explained. Please do listen attentively and make sure that you follow up as the facilitators are taking us through, so that we do not waste a lot of time and we make sure that we deliver what is supposed to be delivered at the end of the course. So once again, you are most welcome. Let me hand over to the facilitators. Professor Balava, thank you very much for being with us again. The floor is yours. Thank you.
Good afternoon, ladies and gentlemen. Thank you very much, Selma, and we also extend our thanks to the Reforum, to the World Bank, to the Institute of Food and Nutrition. We are grateful for the funding and support, and also grateful for the opportunity to invite my colleague, Dr. Thomas. But at the same time, yesterday I was seeing some comments that some people would like a physical training. If you're interested in a physical training, you can always contact us and we make a program. We can travel and come for a physical contact. Thank you very much, and I wish you pleasant and enjoyable training. Pay attention, practice to be perfect. I invite my colleague, Dr. Thomas, to go ahead and present. Thank you very much.
Okay. Yes. Good afternoon, everyone. We are going to pick up from where we left yesterday. But before that, we are going to do the usual ritual when you're using R. I was still going to repeat those steps. Let me share my screen. Okay, now I think I can remove my video. You already seen me. Okay, so we, like I started with yesterday, there are a few things that you need to do when you're trying to do your data analysis using R or any package. The first thing is you need to create a folder for each project, for each analysis that you're going to do. So you create a folder, and in that folder, you put everything, your data assets, your description of the data set. You can have a small README file. You can have your R scripts. So that's the first step. Then the second step is ensure that when you start running R, you make the folder your working directory. It makes life a lot easier. If you don't make the folders your working directory, so every time that you want to call a data set, you need to be able to specify the paths after where the data set is stored. If you're good at programming, that may not be an issue, but if you're a learner, it's better to do things that will make you move faster. Okay, so that is the first one. The second one is that you need to know the packages, the different packages and functions that you require to do a particular analysis. That is not a big deal because you can easily go to Google, but with the time you will also get to know exactly how to go around. So for those who are doing agricultural experimentation, one very, very popular package is what called Agricole package. That was the master's work for some gentleman. After he did his thesis, then he decided to compile it into an R package, and it's one of the most popular R packages that we have around. So you make sure that you know the kind of packages that you want, and then you also need to know whether those packages are installed already or not. If they are not installed, then you need to install them. And we already know how to do the installation. You go to install.package, you type the name of the package, and then you go ahead and proceed. If the package turns out that is not available, that version of R, then you go the longer way. But it's always easy for you to just copy the error that you see in R and ensure that you copy the error, put it in Google, you will be able to see some solution that has been suggested by people. Okay, so we already installed the packages yesterday. So now we're no longer going to install the packages. So always good to make them become like common. So any installation now, we are not going to do. Okay, so after the packages are installed, the next thing is then every time that I do the analysis, I need to call the packages so that they come and they are ready for use. So we are going to start looking at, let's say we don't want the library dev tools. We used it yesterday just for installation of that. So we can start from line number 6. We need Agricole. We need the other one. We need Dobby. We need Lattice. We need Effect. So please always see what is on the screen. There are reds here, but these reds are not the bad one. The kind of just telling you that something is happening. Okay. So if we have all our packages ready, the next thing that we need to do is we need to check whether we have set the working directory. So let's go to, so for setting a working directory, we need to follow the same procedure. We go to session. After session, you go to set working directory. After set working directory, you go to choose a directory. So just see what I have up there. We have session, we have set working directory, and we have choose a directory. Okay. So they are going to share with you another folder, the same link. So you need to check under in the same link. You need to have download week 2, day 1, day 2 materials. Yeah, the folder will be there. So the link is going to be shared. Please don't forget to download. The link is already shared, but we'll keep on sharing. Okay, so to set the working directory, we go to session. set working directory, choose a directory. Okay. So mine is on the desktop. So I go to desktop. I look for, please don't click and don't double click on this to open, because that will mean you are looking for something inside. If there is no any other folder inside, you just highlight it and then you use the open. Okay. So from here, we have set our working directory and everything is ready. So for me, you can see here, let me try to zoom in. Okay, so you should be able to see in the console, this is the command that you use, set working directory, and you can see from there that I've successfully set my working directory. Okay. So now we are not going to run the t-test, and we are going to go and run our analysis of variance straight away. So you check the line where we are going to. So let's go to, my line is 97, 96, 97. So here, I have a simple program. I say running analysis ANOVA using the LM function. So like we stated before, ARA we work on an object in ARA. So we create an object called model 1. And so in this object model 1, we are going to store the results of the analysis here. So here you have LM, which is the linear model. Then just hold on a bit. Okay, so here, okay, I want us to run this. Of course, we are going to see some error also. Remember the data set that we created yesterday was the bond data set. And this data set was created as an object in the memory of ARA. So if we didn't save that, that means it is not there for now. So we first need to go ahead and create the data set. So let's go up. Sorry, let's go up. Okay, so let's start running from, we run from line 43 up to where we finish the data analysis. So line 43, we create an object called A. 44, we run the summary. We got the variance, got the standard deviation. Then we create B. We create the summary, the variance, the standard deviation. You don't need to run the other one. You can only run the one that creates that creates for us the vector. We run 53, 54, 55, 56, 57, 58, 59, 60. We run 62. We run 64, 65, 66, 67, 68, 69, 71, 72, 73. Just run this line until line 82. So you should be able to end up with this. So this is our data set that we are ready to analyze. So as you see from here, we have rep 1, 2, 3 for AAA, rep 1, 2, 3 for BBB, rep 1, 2, 3 for CCC, and so on and so forth. Okay, so we can now skip all this line with the box plot because we saw it yesterday. So let's go now and run our line 97. So in line 97, we are going to do an analysis. We are using the function FLM, which is a linear model. And this is our variable that we want to analyze. We want to compare different treatments. And then the data set that we're going to use here is what we call bond time. Bond time is the last data set that we created. Okay, so let's run. Okay, so have we all succeeded in running up to line 97? Can I see in the chart? There are still a few no's. I don't know why. Agnes Wanziko, can you show us your screen and we see why you're not succeeding? Can you promote Agnes Wanziko?
Agnes Wanjiku.
I want somebody who has not got the thing to show us.
We have promoted Agnes Wanjiku. Please, Agnes, please go ahead and
Has
share.
Agnes been promoted?
Yes, yes, please. Agnes, please go ahead.
Hello, doctor. Hello.
Thomas, you might have to stop sharing your screen, then you allow her a chance to share hers.
I think I know where the problem
Okay,
is.
so we're waiting for Agnes to come and show us the screen.
Hello, doc.
We are
Any
here.
person who has failed to, so that can show us the screen.
Thomas, Agnes is
Hello.
talking. Please go ahead. Go ahead, Agnes.
Okay, I'm saying
Yes.
I don't know whether it's whether I'm slow. I'm slow
Okay.
on type.
Anybody raise your hand if you fail and you want to show us your screen so that they can promote you.
Thomas,
Hello,
Agnes is talking. Agnes, go ahead.
Okay, I'm saying I don't know whether I'm slow in typing. It's typing that is the issue. It's not loading or updating the app
Okay,
packages.
so I can assume that everything is okay and we proceed. The screen is blank.
I think Thomas has a problem.
I can stop sharing my screen and then Agnes shares her screen.
Agnes, you share your screen.
Okay.
Yes, please share the screen.
Okay. You share the screen, go for sharing the screen.
Okay.
Yeah, click on sharing the screen and then we should be able. Sorry, my volume is muted, so I can't hear you talking. Okay.
Can you hear me now?
Yes.
Can you see my screen?
Yes.
Okay, I'm saying my issue isn't loading or something. It's typing because I'm a bit left behind. Like now here, I typed for A and I
No, you don't need to type. You can run the command that we have already given you. The reason why we gave you those because it will save time. Next time, if you want to create your own data set, you're just going to modify the script that we've given you. Don't start typing your own command now because it's going to delay us.
Okay.
Yes, we have the script already. I want you to run the script, not to type it.
Oh, so where is the script?
Hey, but the one you're trying to, it was shared yesterday.
Okay.
Yeah, but you have it in day 5 material. The last, yeah, but you have the scripts here. So why those are the scripts that why are you trying to modify them?
No, I'm not modifying. I'm not modifying them. All these I've been typing them as we go along. But now when we came to creating the bone data, I'm left behind from there.
No, that's why I'm saying you don't need to type them. You have the script already with you. You need to run the script that we have given you.
Okay.
Yeah. So don't try to create your own link now. It's not going to. You're going to be remain behind.
Okay.
Yeah. So later you can modify the script that we have given you to do your own analysis. What you simply need to do, you need to be able to change the names of the files and the names of the variables, and everything will be fine. Okay?
Okay.
Great. So you can stop the sharing now. So you can, okay. So you can go back and open a new script and then continue from there. Okay. Anybody else with the problem that needs to share?
We have a number of hands raised. Maybe, I don't know whether Thomas, you can select. There is Brian.
You just select one of them.
Okay.
Yeah.
So let me promote Brian and Asefa. We have Asefa.
Okay, just get one of them to do, maybe one or two. You promote one of. Have you promoted any?
Yes.
Yes, Asefa.
Asefa, please go ahead.
Can you share your screen and unmute yourself?
Asefa, we are waiting for you. You might be talking, but you are muted.
Yeah, you're muted. So you click on the unmute.
Okay. How about now?
Yes. Now,
Yeah,
okay.
now I can hear you.
Yeah.
So can you share go to sharing the screen so that we can see what you.
Hello?
Yes, can you
Yes,
share
we
your
are
screen?
here.
If you go below, there is something in green says share screen. Click on that.
Okay.
You double click. After you have clicked on the share screen, you need to select the window which
Select the window you want to share.
Is coming.
Okay.
No, Asefa, you have selected the desktop.
Yeah, no, prof, there is some problem with my application. Then let I go back.
No, you first stop sharing And then
Stop
you select
sharing
the
and-
window. First, you select the window which is showing the R. Open the R.
Okay. I will. Okay, come back.
Just stop
Have you
sharing and
opened the R?
start the sharing again.
Stop sharing, and then you open. You select the window which has R.
Right.
First stop, or I can stop it for you. Let me stop it for you. Okay. Hey, no, you have not
Now
stopped.
stop.
I've stopped your screen. Click
Okay.
again share. Click share screen, and then you select the window which is displaying the R. The R window. Then you double click.
Okay.
Click share screen. Have you clicked share
Open
screen?
my application.
Have you clicked
R.
share screen?
Yeah.
Yes. So select the window which has R. Have you done that?
Yes, I've done, but there is some problem happen with my R programming.
So what is happening to your R program?
Maybe you can be guided through without sharing the screen. So
Hey,
please
just you
explain.
the problem. Can you tell me the problem?
Asefa, please explain the problem to the facilitators. I think Asefa has a challenge with the network.
Okay,
So-
so maybe you can promote somebody else, and then I proceed after that.
Okay. So
Before we get someone, can I ask something?
Yes.
Before we promote that someone. So you're saying the script was shared yesterday.
Yes, the script is in the folder that I saw you have the folder. That means you have the script.
So how do I load it now to have the details?
You double click on that script there, the one that is written t-test analysis. Double click on it, then it will open immediately. If you go in that folder for day 5, do you see a file that ends with .r? There's a file
Yes,
with a
yes.
t-test analysis
Yeah.
of.
I have it.
Can you right click on it and say open with RStudio?
Okay. Okay, nice. I see it now.
Okay, so
We-
you
we
can
have-
follow the scripts that you can run the line that I indicated, and
Okay.
then we should be good to go.
Nice. Thank you so much.
Okay.
Okay, we have Amandio Sabonete. Amandio, please go ahead and share your screen. Amandio.
Yes. I
Yes.
have some doubt.
Introduce yourself and where you're from.
I am from Mozambique. I got the degree in nutrition. It's very nice to participate in this program. I
Okay.
hope to learn more about the statistic.
Okay. Yeah. Do you have any challenge?
What?
Are you having any challenge with R such that you can share your screen? Do you have any challenge or there is no problem?
No, in this moment, I can do that. So I'm preparing to make to make it.
Okay, thank
Okay.
you.
Okay, so let me continue then.
We have one more person. called
Okay.
Yasa.
One person
Yes.
comes, and then we can.
Yasa Chisanga.
Hello,
Yes, please, Yasa.
my name is Yasa Chisanga from Zambia.
Yes, please.
Can you get me?
Yes,
Yes,
we are getting you
Can you get
clearly.
me?
Yes, we are getting you
yes.
clearly.
Yes. Can I share my screen?
Yes,
Yes.
please.
Please.
Okay. I've shared my screen.
Okay.
Yes, we are seeing.
So the first thing before you proceed, you see on top there, there is a warning sign.
Which one? Yes, I've seen it. Package.
Packages, agricole car are
Yeah.
required but are not installed. Can you click install? Click on this. What is written install there?
Install.
Okay.
Okay.
Click on that.
Okay. I've installed.
You wait, it's still installing. Are they all installed now?
Yeah,
Okay, you
then
wait until they're all finished. So please always try to read through your RStudio page to see what is going on.
Okay.
I'm sure your problem is related to running the libraries, and they are telling you that they are not found. Okay, can you go ahead and start explaining what your challenges is? As we wait for you for the download to complete.
I think I was trying to run one of them. I think maybe it could have been the problem with the error which was appearing there. I was trying to.
If you try running number 4.
I tried to run. Yeah, I was trying to run number 4, but I was unable to do that.
And you got an error.
Yes.
Yeah, because you need to first install, and then after installing, you can then run the rest.
Okay.
Yeah, you can ignore the number line 5 if you don't have that. You can ignore line 5 for now.
Okay.
Yeah, then you can run the rest. It's going to take a while. As long as you still see the red, you see now it needs to run until all of them are complete. So it's going to take a while. Don't you stop. Let continue running. Don't stop it.
Okay.
Yeah. Okay. So I think we can proceed.
So I can stop sharing.
Yeah, you can stop sharing.
Okay.
Yes, let's proceed.
Okay. Okay, so at this point, I assume that we all have the data, and then we can go ahead and do the interpretation. So the first thing here is we have created an object called model 1, and the object model 1 has several things in. One thing that we can extract from the model 1 is analysis of variance table, and line 98 will extract for us the analysis of variance table. So let's run line number 8, 98. Okay. So do we all see the analysis of variance table? Can I see those who are already seeing the analysis? I want to see those ones who have the analysis of variance table. Okay, I think we have A good number? Good. Okay, we can stop there. Okay, so let's look at the content of the analysis of variance table. So the first thing is on top here, it tells you analysis of variance, and then it tells you the response, which is bond time, and then it tells you that there's treatment. Treatment has 3 degrees of freedom. These are the sums of squares, the mean sums of squares. It gives us the F value, and then it gives us the probability. Now, the other time we say the most important figure in the analysis of variance table is this probability. Now, this probability, we are going to compare it with level of significance, which is 0.05. So you can see from here that our figure of 1.084 times 10 to the power -5. So that means you have 4 zeros before a 1. So you have 0.00001, and then you have 0.84. So this probability here is much smaller than our p-value. This p-value is much smaller than our alpha. So in this case, we say there's significant difference between the treatment, at least the pair of treatment that we are trying to compare. Okay, so that is the first part. So we've generated the analysis of variance table. You know how to interpret the analysis of variance table. We can also generate a summary of the model, what we got in our model. Now, this is a bit expanded and maybe a bit challenging for a number of people. So here, the first thing is it gives us the model that we have run. Then it gives us a summary of the residual. We're saying the minimum residual is -4. The maximum residual is +6. And then it gives us the estimates. So here we have the intercept. Here we have treatment A, B, treatment C, and treatment D. I don't know, we seems to be lacking treatment A. Where is treatment A? Can anybody tell us where treatment A is? Just write in the chat. Somebody did not get the certificate for proposal writing. I also attended, I didn't get. Okay, they said, yeah, I'm getting good example that it's considered as the intercept. So we are making comparison with the intercept. So the intercept, first of all, is going to compare whether the value for A is 0 or not. So you also need to look at the T probability here. So you can see from here that this is significant at 0.000. It's almost so you can see that the value for A is significantly different from 0. And then with B, you're comparing A and B. Then you're comparing C and B. Then you're comparing D and A. Sorry, and A, not and B. Okay, so you can see from here, but I'll give you time to go and you will go and read more. And then down here, you have the residual standard error. It gives you standard error of 3.122, 8 degrees of freedom. It gives you the R square. We're going to talk about R square when we come to regression analysis. And then it gives you adjusted R square, give you the F statistics. So this information here is the information that was in the analysis of variance table. So you can see here, the analysis of variance table, the F is here. Okay. So that is the easier, I mean, this easier part. Now, what we want to do is that we need to check for the analysis, the assumptions of analysis of variance. I'm going to talk more about this when we are going to do further analysis, but I'm going to make a presentation on experimental design and then on the analysis in general. So I'm going to show for you, we're going to look at the different assumptions of analysis of variance. So what we are going to do here is we are trying to check for assumptions of analysis of variance. I've created from line 102, I'm just creating data point 1, 2, 3, 4 up to 12 because there are 12 data points here. So I'm going to create an object. And that object now I'm going to combine it with my data set, the bond data set, so that I can attach. Let me run this, then I'll show you the result first before we can discuss that. Let me do this. Okay, so what I wanted to do, this is the data set that we had before. I just wanted to attach that a point 1, 2, 3 up to 12 to each of these data points, because what we want to do now is we want to see how the residual behaves. We want to see how the residual from each point behaves. So let's create, we've created a new data set. It's almost like the old data, we created a new data set. Okay. One way of looking at the assumptions of analysis of variance, one way of making looking at assumptions of analysis of variance, the assumptions, you can use plots, mainly plots. So we are going to draw several plots, and then from the several plots, we are going to see whether the assumptions of analysis of variance are violated or not. So the first thing is, we want to have 4 different observations, 4 different graphs. We want to plot them together. That's why we use this little command here. So this one will give us 2 rows and 2 columns. Okay, so let's run line 104. Okay. So now we should be able to, I need to create more space so that I can have the plot. Okay, so let me first plot them and then I can zoom them and we can have a look. So you can see here, okay, just hold on a bit. I need to change just hold on a bit. I need to change what I'm sharing. Okay, so do you see my plots? Do you see the 3 plots? Okay, good. Okay, so what we have done here is we are looking at each data point. Here is the plot of our residual. Remember from our summary, the minimum residual was -4, the maximum residual was +6. So, and this is the one that gave us the highest residual. And then this is the one that gave us the lowest residual. And then you can see from here that there is a deviation from the straight line. And what you see here that there seems to be a lot more variation for the bigger values, like at 45. And there's a bit, there's smaller variation here. So we seem to seeing that there is some variation, some violations of analysis of variance. Analysis of variance, one of the assumptions of analysis of variance indicates that one of the assumptions of analysis of variance is that the error term should be constant. The variance in the error term should be constant as you move from one treatment to the other. So we can see from here that there seems to be a lot more variability when you have higher values. Remember when we looked at the box plot yesterday, we found that D had more variability compared to A, B, and C. So this is actually for B, and this is for A and C, and A and C seems to have similar variability. The second plot here, look at what we call, this is what we call a QQ plot. So a QQ plot is supposed to show for us if there is violations of assumptions of analysis of variance. So here we expect to get a straight line at 45 degrees. So from here, well, we seems not to be doing badly off, but there is this data point that seems to be off the rest. So from here, we can see that, well, analysis of variance assumption of normality seems to be okay. And then here, we also see if we plot the different data point, 0.1, 0.2, 0.3, 4, 5, 6. So we seem to see some kind of randomness here, except that this one seems to be a lot higher compared to the rest. So there's some kind of randomness here. One of the assumptions of analysis of variance is that the error term should be random. It should not take any pattern. Once there is a pattern, then you know that there's going to be issue with your interpretation of the results. Okay, so let's proceed, then we'll come back. Okay. Now I want to stop. Okay, let me just first explain my command. So the first thing we did, we created a simple 1 to 12 vector. And then we brought that 1 to 12 vector, we combined it with our original data set, which we call bond data set. We did not want to change the name, so we're just adding it onto the data that we had before. So here then you have your 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then you attached it to your data set that we created before, and then we came up with something that looks like this. Okay, so that's what we did. We just wanted to say, this is our data point 1, this is our data point 2, this is our data point 3. So you can see the first 3 data points are from treatment A, the next 3 are from treatment B, and so on and so forth. Now we want to check what is happening to the residual at point A, point 1, point 2, point 3, so that we can see whether any of the data point that we have is behaving in a strange way. That will help us to check for a few other things. So that is what we did here. And the next thing that we did was we wanted to have we want to have 4 different graphs. So let me first draw the last one, then we can. So you can see we have drawn 4 different graphs on the same page. That is what this function did. Okay. Then once we created the 4 blank spaces to draw them, to draw our graphs, So the first plot, we go to model 1 and we say plot. So which equal 1, there are several plots that you can get in this model here. So 1 is the plot of fitted value versus the residual. And then 2 is the plot of the theoretical plot of QQ plot. Okay, and then this one here, what we are doing with this is we are going to our model here, model 1, and then we are picking the residual. Remember, each of the 12 points has a residual, and then we want to show that what is the value of the residual for each data point. So let me then enlarge this again so that I can explain that. Sorry, I have to change to share new. Okay, so you can see now that what we are trying to do here, we're looking at point A. How are the residual for data for treatment A behaving? There are 3 observations in treatment A. Then how is the residual in treatment B behaving? How is the residual in treatment C behaving? How is the residual in treatment D behaving? So if you look at this point here, this has a higher variability. This is related to the variability in D. And then these 2, A and C, are the ones here. And then B is the one that is there. Remember, B is the one with the lowest amount of variability. B is, no, not variability. B is the one with the lowest bond time, the one with lowest observation. Okay, let me see if there are some questions. Okay. Let me try to address some questions that we raised. Re-explain the interpretation of analysis of variance. I'm going to do that. When do we use analysis of variance table? Analysis of variance table, when you're writing your thesis, there are different requirements. Sometimes people use analysis of variance differently depending on the field in which you are. In most cases, there may not be need to actually show the analysis of variance in your text. You may put it in the appendix. What you're interested in is you want to quote the p-value, and from the p-value you can tell whether there is significant difference or not. But people who do plant breeding are more interested in the sums of squares. So they may go further and try to look at sometimes when you're doing what called genotype by environment interaction, you want to see how the variability in the data is distributed among the genotype, the environment, and then the interaction compared to the error term. So that also depends on the field. So the field in which you're in will influence what you're going to present in your paper or in your thesis. But in most cases, 1 or 2 sentences is enough to explain what is in the analysis of variance table. You can attach the analysis of variance table in your appendix. Can you show how to draw climate? No, we are still doing analysis of variance. Can you please explain the residual versus fitted? Yes. So the residual, so what we have here is that for each data point, we have the measurement that we have got in the field. Remember, for A, we had 27, 28, and 30. And then for B, for C, for D, what we created. Now, then when you have the analysis of variance model, analysis of variance model will make a prediction for each value that you have. So for A, there's going to be a prediction for A. Now, the difference between the actual value and the value that the model predicts for you is what is your residual. Residual is, like the name suggests, is what remains after you've taken away parts of the model. Now, residual is supposed to be noise, supposed to be random noise. And that is why we check for the assumptions of analysis of variance using the residual. The residual is not supposed to show any pattern. Once the residual shows the pattern, that means there is still some information that remains in the residual, and that means your model is not complete. So you need to actually redraw another model. The post-hoc, we're going to go for that. Okay. So the fitted value versus the residual, this one is supposed to show us that there is no particular pattern. But you can see from here that we seem to have higher variability for bigger values and lower variability for smaller values. So this one indicates that this is actually not a random pattern. There must be some issue to do with D, sorry. No, the data point here is I'm just interested in saying this is data point number 1, this is data point number 2, number 3, number 4, and so on and so forth. It has nothing to do with the fitted value. Now, why this is important, sometimes when you're doing field experimentation, you actually want to know what sometimes we can do is then we can get our residue and plot it onto the field map. Now, when you plot the residue onto the field map, you can actually see if there's any strange pattern in the field itself, because there could be a situation where you have residue in one block seems to be higher than residue in other blocks. So that would mean that that particular block has a problem as far as the model estimating the values are concerned. Remember, the best model should be having 0 residue. That means the fitted value and the actual value should be the same. Okay, so we would expect the residue to behave randomly. Okay, somebody saying is getting confused. Afirima, can you tell us why you're getting confused? Can you promote Afarima to tell us why there's the confusion? Can I repeat? What should I repeat?
Afarima who? Oh,
It is very important to find the residual value, because it is the residual that you're going to use the residual to check whether the assumptions are met or not. Okay, I'm going to repeat some of these things. Let's continue running the model and then we see. Yeah. Okay. So let me go back and start from the ANOVA itself, and then, okay, so let's just hold on a bit. Should have muted myself. Okay. So where do you want me to start from the model itself? Okay, let's start from the ANOVA, and then we come Okay. Okay, so. Okay, so from here, we have the analysis of variance table. So the most important thing part in the analysis of variance table is the first thing is the p-value. So the p-value is used to test the null hypothesis. The null hypothesis is stated that there is no significant difference between the means that we are trying to compare. Now, we are going to compare this p-value here with our significance, with our alpha, which is the level of significance. Now, what ARA does for you, ARA goes ahead and does the comparison and it gives you these 3 stars. So, and then the codes is here. It said if it is 3 stars, that means the probability is very small, it's almost 0. If it is 2 stars, that means you're testing at 0.0, is significant at 0.01. If you're testing at 1 star, if it gives you 1 star, that means it is significant. No, I think okay, so you can have significant at 0.01, which is 3 stars, at 0.001, 0.01. So this is 99.9% confident. It gives you have 3 stars. And then 99% confident, it gives you 2 stars. 95% confident, it gives you 3 stars. And then you can have a dot. A dot means it's significant at 10%. And then if it doesn't give you anything, that means the probability is 1. So that's how the interpretation of these stars here. Okay. Yeah. So we don't need to, the F value here is just the mean sums of squares. The mean sums of squares of treatment divided by the mean sums of squares of error. Now, we don't need this to interpret this, especially if we are going to look at the p-value. So the p-value is enough to solve everything that we have here. Okay. So that is the analysis of variance table. And then I went ahead and also got a summary. Let me run the summary. Okay, so the summary here, it tells us the model that we ran. Okay, and then it gives us the summary of the residue. So you can see from here, we have the minimum residue is -4. The maximum residue is +6. And then it comes and gives you the different coefficients. We agreed that the intercept is the coefficient for A because A is not appearing here. So that means any other comparison is going to be versus A. So here we have A. It has a probability of 2.6 times 10 to the power -7. That means it is significant at 0.001%. You can see the stars here. So this table is supposed to continue like that. Then B, now for B, in this case will be you're comparing B with A. Now the estimate is negative because B has a smaller value compared to A. And then with C, we are comparing C versus A. Is negative also means that C also has a smaller value compared to A. And then D, we're comparing D versus A. It has the positive value. That means D performs better than A. So if you look at our graph, you will see the same thing. So this is the interpretation for that. And then, so the stars are given here. So you can have a 0, you can have a 0.01, you can have a 0.00 or 0.001, 0.01, 0.05, 0.1, and then you can have 1. So here, okay. So residual is the difference between the actual value and the value that the model predicts. Okay, so here you have the residual, you have the degrees of freedom, you have the R square and the adjusted R square, you have the P. These values here these last values here are in the analysis of variance table. That's what you have there. Okay. Okay. Okay, so then the next thing then that we did, we wanted to explore the residual. We want to see each of the residual, how they behave. Okay, the lesser, can you promote the lesser to share the screen? He said it's getting error and not getting the same results.
Maybe they can raise their hand such that we are able to see.
The lesser? I'm going to explain what means by which equals 1, which equals 2. I'm going to reach there, but somebody said it was not.
We have promoted the lesser.
Yes, Celeste, can you talk? Show us your screen.
The lesser, please unmute yourself and share the screen.
Okay. Greetings.
Yes, you introduce yourself, where you're from, and you can share the screen.
Yeah, I'm Kitesa from Ethiopia.
Yes, can you share your screen so that we see?
Yeah. It's like this. Where to start?
So what is the?
I don't know. Yeah, yesterday it was working properly.
Okay, can you clean up you clean the console?
Yeah.
Sorry,
yeah.
Can you start running the lines and we see where the problem is?
Which line to run?
Start running your script and we see where the problem is.
Like
No, we are not running that today. Okay.
I think we are here, yeah? Here.
Go up. Continue.
Here.
Okay, you want to run that?
Yeah, I want to continue from this.
Okay.
So I'm getting such type of problem.
Yeah, but you don't have the data. You need to first generate the data set before you can analyze it. So you need to go up.
Up, okay.
Continue up. Start from A. Start from creating A.
Okay.
Go down. Go until where there's A is equal to A is equal to.
Okay, this one.
Yes, start from there.
Okay. So I have to run everything?
Run everything until you create the data set. Then you can analyze that data set. Okay, you can then run, you can run the rest and you will have no problem.
No problem. Yeah, thank you very much. I got it
Okay.
now.
So you are trying to analyze a data set which doesn't exist.
Yeah, that's the problem actually.
Yeah. So Rose Oche said that the results are different. Can you promote Rose?
Oh, now it's okay. Sarah,
Please, the script that we have given you, you can modify it and use it with your data.
Yeah.
Can you stop sharing now? And then, so once you have a good script, you can you don't even need to bother about saving what you've done. The script is enough.
It is enough. Yeah, sure. Okay. Thank you very much. Thank you.
Okay.
Rose, please go ahead.
Yes.
Rose.
Yes.
Yes, Rose, go ahead and
Are you
share.
able to see my screen?
Yes.
So let me enlarge it so that. Hello, Doc. Are you able to see my screen?
Yes. So where's the problem?
Yeah, I've been trying to run my data so that I develop whatever we have with you there, but I can't. Down here, whatever is coming out is different. I'm Rose Ochier from Kenya.
Yes. So can you first clean up and you start clean up the console and you start again?
From here down?
Yes, clean the down one and pull it up a little bit. Clean it up. Just press the brush. There's a brush on top there.
Yes.
Okay. Can you pull up you need to pull to create a little bit of space so that we can see what's in the console.
Yeah.
Okay.
This way?
Okay, so you go, no. I mean down, we don't see okay, fine. So can you, yeah, okay, now you tell us where the problem is. You start running the line which has a problem and we see.
Yeah, I've been running the line, like from library. It was not showing anything compared to whatever you are having, Doc. So, like...
run line number 4 and we see. No, you don't need to highlight. Just click, just put a cursor there, no. That is enough. No, you don't highlight.
Okay.
Yes, that is okay. Go and run.
Okay. Is it?
Continue running then. You've skipped number 5. Okay, continue running. When you highlight library, that means you're only running that part library.
Oh, okay. And I'm seeing some places are having like red marks.
No, that's okay. First go down and we see. No, go down in the console. We see what is the red in the console. You've covered your console. Can you adjust so that the console becomes a little bigger? Yeah, can click on that. No. Click on the big box.
This one here?
Yes.
Okay. Yeah, there are some.
So it's okay.
It's okay.
Yeah, so you can click on the one that shows both of them. Click on the 2 boxes.
Okay.
Okay.
Should I continue running everything?
No, you first go and start running from where we're running today. Go and start where there's A. Go down. Okay.
Yes.
No. Go up.
And over.
Go up. Where there is A equals to. Okay. Yes, I add.
Yeah, 41.
Yes, start with line, line 41.
There's an error.
No, there's
Then
no error.
I go to variant.
Yeah, run everything, run from there, continue running. Continue.
Yes.
Yeah, but I'm trying to tell her she cannot pull it, the thing.
I just continue. Wow.
Yes, continue running it. Okay.
Yes.
So you can see everything seems to be okay now.
I'm very happy. Thank you.
Okay, we are also happy that you are happy.
Thanks.
Okay, so can you then stop sharing the screen? Okay, let me share the screen myself. Okay. Okay, so line 104, I think that's okay. We want to create multiple plots. Then somebody is asking which equals to 1. Now there are 4, 5 plots, different types of plots in the model, in model 1. Now, which means you're saying out of the 4 that you have, you plot for us one. And then the second one say plot for us 2. 1 is the one that is fitted value versus residue. 2 is the one that is the QQ plot. Okay. So you can have 3, you can have 4. So you can replace which equal to 3, which equal to 4, which equal 5 and C. Then it may not give you, it may tell you you don't have it. Okay. So you can run these lines and then you have your, so let me try now to re-explain the residual, and then from there we can proceed. Okay, so plot 1 is the one that you have fitted value versus the residual. So remember, for each observation, there is the value that you've measured from the field. And then when you put it in a statistical model, the statistical model also predicts for you a value, that this value should be that. Now, the difference between the actual value from the field and the residual, the value that the model predict for you, that difference is the residual. A good model should have a 0 residual. That means what the model predicts and what is in the field should be the same. But in most cases, that hardly happens. So residual then becomes important to tell us what is going on. So you can see from here that this point here, this point number 12 here, for example, it has a much bigger residual from 0. 0 is the ideal. You see the point that are close to 0 mean are the one that are predicted very, very accurately. So this one here has a much higher residual compared to the rest. So this point is not, this particular model does not seem to predict point number 12 well. Okay. And then for the second plot, that's the QQ plot. This is a plot that shows if there is normal distribution. Remember, the residual is supposed to be normally distributed with a mean of 0 and a mean of 0 and a constant variance. So this will tell us that, well, we are actually okay. This doesn't seem to be very bad. And then the plot for residual versus data point, I just also wanted to show you which point is giving us the highest residual. So point number 12 is the one that gives us the highest residual. So I may want to go and check at this point here and say, why is this particular point not predicted very well? Why is the model not predicting this particular point well? So that's what you're going to check. But later you may also want to check whether this point is actually influencing, is an influential point. Okay. And then here we also decide to actually plot a box plot for each the residual for each treatment to see the amount of variability that exists within each treatment. And we see whether the variabilities are constant. Remember, one of the assumptions of analysis of variance that the variance should be constant. So you can see that there's a lot more variability in D, which is actually what is reflected here. You can see there's a lot more variability in D compared to the other cases. And then you can see from here that there seems to be, at least they all have positives and negative residues, positive and negative residue in each of the different cases here. Okay, so I hope that makes the explanation a lot more clearer now. Okay, so now we are going to proceed. So I'm going to show you another plot. What we are first going to do, I want you to go and run line 110. I want just to have only one plot. I don't want to have more than one plot. There are different ways of doing this, but I always try to get a simpler way that I can use to do my illustration. So let's run point 10, 110, and then I'm interested in line 14 to 120. You'll see what will happen. So let's start from line 14. Okay, so you can see from here that we plotted an histogram of the residual, and then on the histogram of the residual, we have imposed a normal distribution curve. So here, this can help us to check whether actually the residue that we have has a normal distribution or not. So here, well, it's not that bad, but the problem that there's some gaps in the data. But here we can see that our data is fairly normally distributed. So the assumptions of normality is not violated in this particular case. Okay, so please, you cannot, these things are being recorded there on YouTube. So always, you can always go on YouTube and revisit and learn more and more and more. Okay, so we looked at the residual plots, and residual plots is giving us some information. So we can, we can go ahead and actually test whether the residuals are normally distributed, whether there's, okay, so we have line 123, and please note that we have an explanation here for what we are testing. So here we are testing for homogeneity of variance among treatments using analysis of variance approach. ARA can be notorious for having what we call, you have one set of function inside another. So here we have, the first thing that we want to do is we run our analysis of variance. Okay, once you've run the analysis of variance, you extract the residue from it. Okay, and then you square the residue that you've extracted. Okay, and then you then fit the residue that you have here, that you now try to analyze that residue with the mean, with the treatment from the same data set. So you're running analysis of variance. This is similar to what we started with. You see, we started with this model here. So what we could have done, we could have just picked this one here and put it inside. So the whole of these can actually be replaced with model 1 that we have. The whole of this can be replaced with model 1. So I can actually type model 1 there. Maybe let me just do like this. Okay, because the whole of this is what generated for us our model 1. Then the next thing is we go to our model 1, we pick the residual from our model 1, and then we square that residual, and then we use this actually as our variable that now we need to analyze using the treatment. So we are comparing variability in the residual for the different treatments. So we can run 125 should give us the same answer as 124. Okay, so here you can see. So can somebody tell us, is there a significant difference in the variance among the treatments? Can I see in the chart? Hey, I'm asking, hey, can somebody explain? I'm not asking you to say no. If you can explain, you can try it for me. Hey, okay, I think the one who the no is correct. Yes, sorry. So here we can see that the p-value here is greater than 0.05. So we reject the null hypothesis. We fail to reject the null hypothesis that the variances in the four groups are significantly different. Okay, so our p-value is bigger than 0.05, and therefore we cannot reject the null hypothesis that there is no variation between the treatments. So the variance in treatment 1, the variability in treatment A, treatment B, treatment C, treatment D, although they appear to be different, but when you test it statistically, there is no difference. Now we can proceed and test. We accept the null hypothesis. We can proceed and go and do 11 tests. So 11 tests also will test for us for homogeneity of variance. Okay, so let's run line 128. So are the variance in the three group homogeneous? So do we reject the null hypothesis or not? Okay. Yeah, so there's no difference between the variance. So you can see that both the Levin test and the analysis of variance test seems to tell us that there's no significant differences in the variance of the different groups that we have there. Okay. Then we can go ahead and test. Okay. So there is what we call a rule of thumb. There's what we call a rule of thumb. So although the analysis of variance may not be showing us significant, although the Levin test doesn't show us that there's significant differences between the different variants, the variance in the different group, what we can do is we can look at the ratio of the maximum variance to the minimum variance, and it should not exceed 5. Okay, so let us first try to run line 131, and then I can explain from there what's going on. So what I want to do here, I look at aggregate. So what aggregate will do, aggregate is going to get for us bond time, and then we'll analyze it for each treatment separately. And what we want, the summary we want is the variance. So let's run this line. Okay. If you could not find Levin test, that means you did not call one of the functions that one of the packages at the beginning. So can you go up and run those libraries so that you can get the packages? Otherwise, then you will not be able to Okay. So who can tell us? Oh, the snake sign is called the tilde, is a tilde, it's a Greek letter called tilde. So it's saying, like you're saying this, in terms of aggregation means say you aggregate them, but we also use it for running the model. So this is the relationship. That's what you use to start a relationship between this and that. So you're trying to use treatment to study the different. So for the different treatment group, you want to divide the bond time data and get the variance for each group. Okay, so what I want you to do is I want you to calculate what is the maximum variance in this case. Can I see what is the maximum? Which one has the maximum variance? Okay, D has the maximum variance, and which has the smallest variance? So A and C will have the smallest variance. So let you divide, I want you to divide the maximum variance with the smallest variance. Divide the maximum and smallest, what do you get? Say you get 14. Okay, so since we get 14, okay, so 14 is actually greater than 5. So we cannot ignore the variability that exists in the different treatments. Okay, so let me run line 132. So I run line 132. Line 132 gives me 12. But you guys, I think your calculation is not okay. Let me see. 28 divided by 2.33. But your line, your 14 is not correct. You gave me a wrong answer. Okay, so this is also a very simple command that we work here. So what we want to do here, the first thing, the upper part here is to get the maximum variance, and then you get the minimum variance, you divide, and then you get your 12. So, and this is just a simple, why divide A by, why D by A? No, we're dividing D by A because the rule of thumb says you check the ratio of the maximum variance to the minimum variance. It should not be more than 5. That's what the rule of thumb says. So in our case here, this value is more than 5. So we can see that there is a significant difference between the variances in the groups that we are dealing with. Okay, so you have the script with you. You're going to run, and then we're going to move on. Okay, so let's look at another test. We are looking at the test for normality. So you can use the Safiro.test to test for normality. So here, what is the likely effect of variance greater than 5? What we are saying in this case is that when you're trying to compare a group that is highly variable compared to a group that is not very highly variable, the comparison becomes very unreliable at some point. So at some point, you may actually get different results. Okay, so what we are trying to do here is we are looking at, remember the thing is the assumption is that the variability in the different treatment, the results from the different treatments are uniform. So we are trying to compare, the quickest way to look at it, whether it is uniform or not, is to look for the highest variance with the smallest variance. The rest in the middle you can ignore, because once the highest and the smallest, the highest and the lowest are different from each other, that is enough already for you to say the variance are not the same. Sylvester, you've just connected the laptop. Yeah, don't worry, you continue, you follow. Okay. Eric, what can I do? Eric, what is the problem? Zafiro test for normality, test for whether the residuals are normally distributed. Okay, so let's run line 135. Yeah, you can also use Bartlett's test. There are different tests that you can do. Okay, so when you look at the Zafiro test, do we confirm that there's normality or no normality? The null hypothesis is that there is normality. So are we rejecting the null hypothesis or not? We are not rejecting the null hypothesis because the p-value is greater than 0.05. Okay. And then, okay, I think we're doing great. I'm going to run just one simple, and then we'll have a break. Okay. Yeah, if you cannot find Levene test, that means one of the packages up there, you've not brought it. Why can't you run Zafiro test? Yeah, there are a number of questions that you can also ask Google and gives you the answers. Yeah, if you set your console to false, of course, then you will not see any results there. Okay. We are still going to come back and do a little bit of this other test again. After I talk about experimental design, I'm going to run again another sets of analysis, and then from there we will continue. So this test, I'm going to run them again. So let's try to run a post hoc. So when we looked at the analysis of variance, let me run the analysis of variance table first. I want to get analysis of variance, and then I want to use that to explain something. Okay, so from the analysis of variance, when you look at the p-value, the p-value has 3 stars. So with the p-value with 3 stars, that means we are 99.9% confident in our rejection of the null hypothesis. So when we reject the null hypothesis, the conclusion that we can come up with that at least a pair of the treatment that we are trying to compare are significantly different. Remember, we have A, B, C, and D. So you can compare A and B, A and C, and we say at least a pair of those are significant, but it doesn't tell us which ones are significantly different. So let me go and run a post hoc should be the one to tell us which of the pairs are significantly different or not. Okay, so we're going to run a two-way analysis of variance later on. I will explain that. No, I think I already explained why I created a data point. The data point, I just want to know what's happening at each observation. How does each measurement works? The null hypothesis in the Levene test The null hypothesis in the Levin test is that the variance among the different treatments within the different treatments are equal. So equal variance is the null hypothesis. So if we fail to reject the null hypothesis, that means we conclude that the variance are equal. Okay, how do we get or receive the training certificate, please? That one will be answered by the forum will answer that. Which test should we do on the data in case the variants are uniform? That's we will talk about that. You couldn't find the function lsd.test. Did you install you need to go up here. Let's go up and look at the different. So once it tells you that you don't have the function, that means you're not. Try to run Malcolm 11, my 11. That has the LSD test. Okay, so let's try to. Okay, so let's look here. So after running line 138, you can see it tells us the least significant difference is 5.87. And then treatment with the same letters are not significantly different. So here you can see D as letter A as letter B, C as letter C, and then B as letter D. Each of them have different letters. So that means they are significantly different from each other. So all the pairs here are significantly different. So you can see here we are doing what we are doing here is we are comparing the first one and the second one, the third one, and that. Okay. Now you can also adjust for what we call Boniforoni. So what happens here is that because of making so many comparisons, like you say A and B, A and C, A and D, then B and C, B and D, then C and D. In the process, you can commit what we call type 1 error. So even if the F statistics does not show significant differences between the treatment, if you go ahead and do your LSD, sometimes you can actually find out that they're actually significantly different. And that significant difference comes about because what we call multiple comparison. One of the examples that I'm going to run is going to show the multiple comparison, how it comes in. So let's run 139. Okay, so you can see now that the minimum significant difference have now increased up to 8.869 or 8.7. Now, if you look here, A is different from B. A is different from D. They don't share the same. A is different from D. They don't share the same letter. But A and C share letter B in common. That means they're not significantly different from each other. And then C and B also share C. That means they're not significantly different. So once we do the Boniforoni correction, you can see the result changes. The Boniforoni correction is a lot more stricter. So what we got before as significant has actually now stopped being significant. Remember, in the first case, everything was significant. But once we change and we render Boniforoni, then you can get all these differences. Okay? LSD is not equal to Tukey. Tukey is also kind of has a correction in itself. There. Okay. Okay, so let's start from line number 138. So in line 138, we are using LSD.test. We are looking at our model 1. And what are we comparing? We're comparing the different treatments. And console equal true means we want to show the result on the console. Otherwise, the result will not be shown there. Okay, so let's run this. So based on this, you can see the letter A, B, C, and D. And here it is stated clearly that treatment with the same letters are not significantly different. So what happens here is then we use the LSD here to compare the different treatment. So for example, if you compare the difference between A and B, this difference here is greater than the LSD, which is 5.86. So with that, we can declare A and D to be significantly different, and we make them to have different letters. So if this one has letter A, this should have a letter B. Then we can compare A and see if they're not different. We can also give them different. So here you can see the difference between A and C. The difference is 8. 8 is still greater than 5.8. So we can consider them to be significant. Now, when you come to this also, the difference is also about 8. That's why you have different letters. Now, if we run the second one, you see the second one now, we are now using something called minimum significant difference. Minimum significant difference in this case now has a value of 8.7. Now, if I compare this A and B, okay. So if you compare A and D, you can see that the difference between them is still greater than 8.86. But once you compare A and C, you can see the difference between A and C is 8. 8 is less than 0.87. So that's why now they're having the same letter. If you compare this, C and B, you also, the difference between them is also less than the minimum significant difference. Now, why do we adjust for Boniferroni? Now, what is happening here is that when you have, in this case, we have A, B, C, and D. Okay, so that means in terms of pairwise comparison, I'm just writing this. We need to compare A and B. We compare A and C. We compare A and D. We compare B and C. We compare B and D. P and D. We compare C and D. So you see now, when we set our significance level at 0.05, that every time that we make a comparison, that level of significance is 0.05. So at the end, you're going to accumulate a lot of errors, so that by the end of the day, your type 1 error is going to increase, is going to get a lot more bigger. And there's a high chance that even what is not significantly different may actually be declared to be significantly different just by simple error, by chance alone. And that is what we have actually seen in our case. Now that when you adjust for Boniferroni, what you're simply doing, you're becoming a lot more stricter. Instead of having your alpha to be 0.05, we can, for example, divide alpha 0.05 by say how many pairs we're comparing. In this case, how many pairs did we compare? Let's say by 4. So our alpha now going to change to 0.0125 instead of 0.05. So we become a lot more stricter when you're making the comparison. So there are several adjustment that can be done. There is the surface, there are a lot more. You need to read in the literature, you get them. Okay. So we can now run our example number 2, which is very quickly because we have the same thing. So the first thing we have done is to create the data set. So let's run line 145. I'm not going to do a lot of explanation here because what we have here is similar. Always check what you've created. Okay, let's have 10 minutes break. We start at 4. Yes, both Bonferroni and Takis are different ways of correcting for multiple comparison. Okay, so we are starting after 10 minutes. I'm going to mute myself, so don't expect me to be saying anything. wants to share the screen?
Thomas, you said who wants to share?
Okello Remigio.
Oh, okay, Okello Remigio.
Okello.
Okay, we have promoted Okello Remigio.
Okello Remigio, Kidi, yes.
Yes.
Okay.
Okello, please share your screen. I think there is a challenge with the Okello's. Yeah. Oh, he is now joining.
Okay.
Okay. So Remigio, please share your screen. Remigio, unmute yourself.
Yes.
Yes, please go ahead.
Hey, where should I go from here?
You go look down, there is sharing screen.
Okay.
In green. Then select the screen to share, which should be your ARA Studio.
I'm not, wait.
Do you see something down, read share screen in green?
Yes.
Yeah, click on that.
Click.
And then select which screen you want to share.
I select my screen, isn't it?
Yeah, the one you want to share. There are many, there will be a number of screens showing up on your on what you then you select what, double click on one.
It's still showing a number of names of participants here, not like it is just there is a markup of greens.
Yes, you click on the markup of green, which share screen.
Yes.
What does it tell you? It should give you some a window that you can select what to share.
I'm seeing something now. Okay, ARA Studio, eh?
Yes, you share the ARA Studio. Click on it, then click share.
Yes, this is my screen.
Okay, it's coming, not yet, but it's going to come.
Yes. Are you able to see it?
A full screen. Okay.
Yes.
So where's the problem?
Until now, I'm trying to run the. You said we ran over number 40. I've tried to run it. Okay, I started from the library. Yes, when I ran.
You ran all the libraries?
Yes.
Okay.
Yes, let me first take you here. I'm seeing a lot of errors.
First clean up which errors. Some of them, not everything in red is error.
I should clean everything here.
Okay, clean. Can you run from from 4?
Yes. Yes.
You skip 5.
Pardon?
Go to 6.
Hello?
Go to 6, run number 6, line 6. I said you go to number 6.
Number 6, okay. I run.
Yes. 6, 7, 8 up to number 11.
From number 6 then to number 11.
No, run them until 11.
Okay. All right. All right. Okay. I see how it is coming.
No, but you need to wait for, okay, you need to wait for the, okay, that's fine. Have you run the last one?
Up to 11, yes. CG plots too.
11 is not, go to 11
Hey.
is not yet run. Run the
Yeah,
9.
yeah. Okay.
Okay. Can you go down, then go to where A starts from, where the bonds?
41 is where A is.
41.
Yes.
Can you run from number 41 onwards?
Okay.
Just continue running.
Okay. You'll tell me where to stop. Eh?
Just continue running.
Okay. I think I'm seeing something interesting.
Continue.
Yes.
Yeah, continue running.
Yes, yes.
Run.
Now I've started seeing some error down there.
What did they say?
Are we still safe, doctor?
No, where's there? We don't see, we're not seeing anything. We're not seeing data. Okay, the margin is that's okay. What you need to do is can you click on you see the thing
I'm
is that
meaning
where
this
the-
one
where
down.
the
Eh?
not
There is
supposed to
error
be
in plots.
smaller. So you need to adjust that pattern, make it bigger. Can you click on the there is on the extreme, is that box, there's bigger, there's a smaller and a bigger box on the extreme, or where the graph is, not there,
Where?
on the extreme end.
Here?
Go along the same line. What? No. You saw the box down, you saw the box above the fourth, go on the extreme, the fourth window, there's also a box on top.
This one.
Yeah.
Okay.
Click on that. Can you adjust the left hand, try to pull and make that one bigger.
Okay.
You're doing it wrong, push it the other side.
Okay.
Continue. Okay. Can you now try to run line 104?
Yes.
Okay.
Yes.
You run.
I run, but it's showing some error.
It's again showing the same error.
Hey, I'm seeing something here.
No, you go ahead, continue running. There's no error there.
Okay. I ran one. Okay.
You continue running. No. You check. Okay, the 5 is not okay. Yeah, run the other one. The 5 is okay. The 5 does not run. You need to change that to. You can remove the 5. Just run 1 and 2.
Okay. Then I run this again.
Yes. And run also that.
Okay.
Okay.
Hmm.
Yeah, so you can continue running the rest of the line. There should be no problem now.
Okay, thank you. Then you box.
So you run quickly and we see what is coming on if you want us to run, to continue staying there.
Okay.
Okay, you can now stop sharing the screen and continue running on your own. You're okay now.
Okay, thank you.
Okay. Okay, so let us now run the remaining. So can we start running now from line 145? Just let's run line 145 up to, you should be able to get the plots that we've done before. So we run 141, 145, 146, 47, 48, 49. Okay. So look, the green part is explaining to you what you are doing. So we can have a summary of yield. Okay. So let's run 153, 154, 155, 156, 157, 158. Okay. Then what we do, just highlight the irrigation data and run that alone. So what we all did there, we're just creating this data set here. So here you have replicate 1, 2, 3, 4, 5 for treatment, no irrigation. Then you have 1, 2, 3, 4, 5 for irrigation method 1. Then you go for irrigation method 2, irrigation method 3, irrigation method 4. That is what we have done. All the steps that we have done. The first step was to create the yield. Then we created treatment, then we created replicate, and then we brought them all together. Just like what we did, in the previous one. Okay. So once you've created your data set, you first need to ensure you've created the correct thing. So you need to print it and see what is going on. So let's look at the names of the columns. So this one will tell us that there are 3 names, there are 3 columns. The first column is called replication. The second column is called treatment. And then the third column is called yield. We can also check the first 6 observations. So you can see the first 6 observations. Okay. So what we are running here is the same thing that we ran with the first data set. I just brought a new data set so that we can see some of the differences. You can look at the structure. So we'll tell you that this is a data frame with 25 observations on 3 variables. The first variable is replication. It said it is character. You can see everything is put in the quotes, double quote, that means it's character. And then the second is treatment, which is also character. We have everything in quotes. And then the third one is yield. It's also telling us it's character. But remember, the yield is supposed to be numeric because that is what we are analyzing. So what we are going to do now is we are going to modify our data set. The first thing that we need to do, we need to convert replication and treatment into factors. And then we need to convert yield into numeric using as.numeric. So we can print and see what we have done again. Okay. Then we can also check the structure of what we have done. If say object irrigation data not found, that means you've not created it. So please go and run the previous step before you can run. That means you skip some step. Latif, you first go and run the other step before you come back. You will see the error will no longer be there. Somebody say, why not make 5 observations? If you want to make 5 observations, then you can put head, the name of the data set, and bracket and a comma, then you put 5. I don't know what the person was thinking when he said you observed the first 6 observations. Okay, so we've seen now that we still have a data frame. Is the first observation is called replication. It is a factor now with 5 levels. The levels are 1, 2, 3, 4, 5. And then the second column is treatment. It's also a factor with 5 levels. And then the last one is yield, is now numeric. Okay, so we can go ahead and then do the aggregations. We aggregate. Okay, so this is the same thing that we did. So you say for treatment 1, the minimum yield is that, the first quartile, the second quartile, the medium yield, the mean yield, the third quartile, and then the maximum yield. So you can run this for round 170, 172, 71, 72, 73, 74. So this one is good because this one will give you kind of a good summary that you can use. At least it will tell you a few things about your data before you start the analysis. So let's run a box plot. That's 179. Okay. So based on the box plot, let me try to first expand a bit and then ask you a few questions. Okay, so you can see from here, that is method 1, method 2, method 3, method 4, and the method of no irrigation. Which method produced the highest yield? Okay, so method 2 produced the highest yield. Do you think there's significant difference between method 4 and no irrigation? What can you say about the difference between, the likely difference between method 4 and no irrigation? Okay, you think there's no significance, some people there's. Okay. Okay, so what is clear from here is that method 2 seems to be completely off on its own, and the other method seems to not fare very differently from the no irrigation method. What can you also talk about the variability? There's a lot more variability in the new method. There is very little variability in new method 4. Okay, let me change the screen and go back to my RStudio. Okay, so we can also look at the yield by replications. So we seem to see there is one particular values that are up. What could be the value with what could be happening to the values that are up? Can somebody tell us in the chat? Somebody said they're outliers. Okay, but from which treatment do you think they're coming from? Yeah, they could be coming from treatment 2. Remember, they could be coming from treatment 2, which is the one with the highest yield. So these are the other 4 methods, and this should be the 4th method, the method 2. So you can actually see. Okay, good. Then we can go ahead and run our model number 2. Do the summary. And then you can see from here that the p-value said there's significant difference between the different, at least between a pair of treatment, a pair of irrigation method. We can look at the summary, just like we did before. We can also go and do the residual plots. It should be a lot easier now for most of you. Oh, sorry, sorry, I need to first draw again. M4. Okay, I want you remove the 5 for now. I remove the 5, the plot 5, and do the 1 and 2. 1, 2, that, and then let's do one of the box plot first before we can run 196 so that we can compare 4 observations. So I'm going to change the screen that I'm sharing so that I share the Zoom one and we have a look at. Okay. So you can see from here that the values here are closer, the values here are closer, but there is one where there's a bit more variability. And the one that has more variability seems to be the one with the value that's around 200 kilogram. So this is the one for treatment number 2. So you can see that treatment number 2, which has the highest yield, is also the one with a lot more variability compared to the other treatment. These are the ones that are together here. Now, if we look at the normality assumption, we seem to be doing well. If you look at the randomness, yeah, this is also seems to be okay. And then you see now method 2 is still one with a lot more variability compared to the other method that we are looking at. Okay, so you should then be in position to interpret this without really having any problem. Okay, so let me continue. I want to use the last 30 minutes to introduce an experimental design, which we'll summarize tomorrow and then do. Okay, so we can go and run line 195 so that we can just have one plot at a time. So you can see this is the residual versus treatment, then residual versus replication. We can also plot our histogram. Okay, you can see your beautiful line here. So also this one tells us that, well, seems to be no problem with the normality. We seems to be doing well, although there seems to be a bit of a longer tail this side compared to the other side. Okay, then the same test that we did before for homogeneity of variance. So here the p-value is 0.0658. So are we rejecting the null hypothesis or not? Can I see in the chart, are we rejecting the null hypothesis? Okay, so we are not rejecting the null hypothesis. That means the variances in the different groups are equal. Good. You guys are now becoming super students. Okay, so let's run a Levin test. It should confirm what we had before. So the p-value is less than 0.005, is greater than 0.05. So also we don't reject the null hypothesis. So in this case, we say the variants are homogeneous. But let's run the rule of thumb. We look at the maximum versus the minimum. So the maximum variance is 2 in 2, and then the minimum variance is in 4. So if you get the ratio, you have 393.46673 divided by the smallest, which is 30.76787. Okay, we have a value of 12. So this one also is greater than, so if you run this line, these two lines, you have a value of 12.78. So this, by rule of thumb, we actually look at this value is greater than 5. So even if the two tests above indicate that there are no significant differences in the variances within the different group, but the rule of thumb seems to suggest otherwise. We can do a superior test as well. And then we can do our LSD. So you see the LSD now talk about A, which is number 2. Okay, it's different from all the rest. But number 1 and 2 and 1 and 3 are not different. And then, but 4 is not different from, the no irrigation, but 4 is different from the others as well. Now, if we do Boniferroni correction, let's see what will happen. So you can see with Boniferroni corrections, things have changed. So you can see that A is different from all the rest. 1 and 3 are not different, but 1 is different from 4 and no irrigation, while method 3, method 4 and no irrigations are the same. They share the same letter. Okay. You're getting error because you need to go and you first need to go and run the Malcolm. You go and call the library Malcolm. You need the library Malcolm, please. Leonard, you need to. Are you back in Kenya? Okay, so that was what we had before. Okay, so now we can run what we call randomized complete block design. So in the other case, we assume that there was no blocking. I'm going to talk about blocking when we are talking about experimental design. So we can also run. Three 231. Let's run 231 upwards, not downwards. Always check what you've created. Look at the structure. Change the bonds to numeric. Change the bond dog type to factors. Change bond type to factors. Check you again. People are insisting on registration link. Okay, so now you should be able to run this without any problem. You can run your box plot and you can check which one seems to be higher than the rest, which one has more variability. Okay, so you can see that there's the big dogs take shorter time to crush the bond. The small dogs take a longer time to crush the bonds. But there's a lot more variability between the longer and the smaller and the medium-sized dogs in crushing the bonds. Now we can go ahead. So here we have two things. We have the types of the dog, and then we also have the type of the bonds. Now we're going to run a simple model number 3, which requires, we're just running it. We want to explain the time taken by a dog to crush the bone. You want to explain that time by using only the type of the bonds. You want to see where there are differences between the types of the bonds. Now, in the second model, we want to see whether there's difference, there is the type of the bonds, but you also want to take into consideration the fact that there are different types of dogs. I'm going to show you in my experimental design how, I'll talk a bit about this toy example mine that I like using frequently. Okay, so we are going to run model 3 and model 4. Okay, we're going to check for the, okay. So you can see from here that for model number 3, look at the p-value is 0.0881. So is there a significant difference between the type of bonds? I want to see in the chart, is there a significant difference? No, great. Good. You can now stop typing. Okay, now let's look at ANOVA for that. Okay. Now what happens now? Is there a significant difference between the type of bonds? Okay. So after correcting for the type, after taking into consideration the types of the dog, you now see that the bond type becomes significantly different. So that means if you don't correct for the type of the dog, you're going to have your error, your residual error to be much bigger. So you can see from here that the bond type is significant, and then the type of the dogs also significantly different from each other. Then you can go ahead and look at the residual like what we did before. So it's still the same. You can allow me to crush now because I think we've done this, so that we also become advanced like it has been promised. So we need to advance slowly and surely. So we can run from 263. Okay, so what I'm trying to do here is we are trying to compare plot 1 for model 3 and model 4. Then we are going to compare plot 2 for model 3 and model 4. Okay, so let me just expand this, and then I share the screen and we try to explain what's going on there. Okay, so first thing, if you see here, you can see that here there is a straight line, but here there seems to be kind of a pattern. You can see the residual seems to be moving in this direction and forming some kind of a curve. So from here, you can see that here we don't seems to have a big problem, but there seems to be a problem here. The model that we are using seems not to fit the data properly. Now let's compare model 3 and model 4. We have the normality seems to be okay in both cases. This is fine, this one is fine, but this one is telling us that, yeah, I think there's some kind of lack of fit in our model. So you can see for smaller values, the errors are positive. And then for larger values, the errors are also positive. And then for values in the middle, the error seems to be closer to the center, closer to 0. So here the estimation seems to be okay, although they're also below. They're also negative, they're kind of negative. So we seem to see some kind of a pattern in our data set. Okay, let me stop sharing and I'll share the next one. Okay, so we can also run line 271, which is for model 3. We can run the same for model, oh, this one said dog not found. I think it's dogs, there's an S is missing there. Okay, then we can also run their box plot for the 2 models, and then we can compare them. So let me zoom. I change to the zoom one. Okay. So what you can see from here is that for model number 3, if you look at the first 4 dogs, their residuals are negative. Then the next dogs, they have residuals that are close to 0. Then the last dogs have the residuals that are positive. Now, this is a clear indication that there is lack of fit here. There's a pattern in this, so there's lack of fit here. While if you look at the residual here, we seems to see there's a distribution, there's random distribution going on in this particular case here. Now, if you look at if you look at the bond type, yeah, we seems to be okay. For model 3, well, we still have high variability here and there, but model 4, we seem to have a very good fit for A, very good fit for C, and also a good fit for B, but the fit for D seems to be a little bit off. Now, these are the things that you need to look at when you're doing your data analysis and try to get an explanation as to what is really going on in your data set. Okay, let me stop this, then we can So we can continue the different plots, but I'm not so much interested in these plots anymore. You can go and look at them, but let me just have them ready, then we can just compare them. Now you can see the importance of putting putting this plot side by side. By putting this plot side by side, you should be able to actually make your comparisons of the model a lot easier than if they are not side by side. So you can see from here that for big dogs, the residuals are all negative. And for small dog, the residuals are all positive. It's only for the medium-sized dog that we have both negative and positive residual. Now, this is a clear sign that for the smaller dog, the difference with the model is under the model is overestimating the time that the dog takes to crush the bones, while for the small dog is overestimating. The model seems only to work fairly well for the medium-sized dog. Now, if you take the type of dog into consideration, that is for model number 4, you can see that they are all now above and below 0. So there is no pattern. The pattern that we saw here completely disappeared. So the pattern that we see in model 3 is because we did not include the dog type in our model. Once we include the dog type in our model, then the residual now becomes random. And you want residual that is random, not residual that is not random, that is non-random. So the distribution, the normality is fairly okay. In most cases, normality is not a very big challenge as far as analysis of variance is concerned, unless the sample size is extremely small. Analysis of variance is a bit robust to violations due to normality, but the main challenge is always the issue of non-constant variance. Okay, let's see whether there's some question. Okay. We have a few minutes to go, but that's fine. Let's run the remaining script. Okay, so we can still repeat the same test. You can run this. I'm not going to explain it anymore because we know how to explain. Okay, what I want to do now is let's look at the two model, look at the post hoc. So here you can see A, so that means D, A, and C are not significantly different. They all have A, but B, C, and D all have B. So the only difference here is that there's a difference between D and B. There's a difference between D and B. And then these other ones are not different from each other. Okay? Now let's run when we adjust for Bonferroni. Now when you adjust for Bonferroni, you see everything now is not significant. Okay? Because now Bonferroni becomes a lot more stricter. So sometimes if you're too strict, then you may actually miss out. Now let's look at our model number 4. Okay, so model number 4 seems to indicate D being different from the rest, while the other ones are all the same. Now let's look at the adjustment and see what will happen. Okay, when you adjust, it's still the same. So that means the difference, you see D is actually far apart. So it doesn't matter whether you change the Bonferroni or what, they will still have that significant difference that we're talking about. Collins, when do we use Holmes' method of adjustment? I give that to you as an assignment. Now you go and read. Now I don't want to bring it here. And tomorrow, the first thing tomorrow in the morning, Colin is going to explain for us when you're going to use homes. Okay. Okay, so the same thing here, we have another data set, so you can also run this. I think we're just going to run this and finish, and then we call it a day. So we've had a lot of example here for you to actually appreciate analysis of variance. This is one way analysis of variance because we are only having one factor, but we can have, we're going to look, tomorrow we're going to look at two-way analysis of variance. We may also look at how you analyze a data using, how you analyze a split plot and so, but depends entirely on the time that we have. So we can run this. Now, this is a lot easier because we have created our data set in R. So you don't have this error of trying to bring in the data and all that. But tomorrow we are going to be getting data that is already saved, and we're going to continue. We're going to analyze them. So we can look at the. Let me share the plots here. The Zoom. Yes, please. Please put your question in Q&A. Don't put them in the chat room. People put a lot of things in the chat room. Okay. So if we see here, you look at A. So the variety seems to be, the performance of the variety seems to be very uniform. I mean, there's really little variation among them. There's a lot of variability in variety B, I think. There's some variability in variety E. Now, when you look at the blocks, block 1 seems to have measurements that are quite uniform. Block 2 seems to have more variability, followed by block 3 and then block 4. So there's low variability in block 1. Okay, so we can go ahead and run our model 5 and 6. This is similar to what we did before. We ran model 5 with variety only and model 6 with variety and block. And then we can go ahead and explain, look at the differences in the results. Okay, so you can see from model 5, the varieties are not significantly different because the p-value is greater than 0.05. Let's look at model 6 and see whether there will be any change. For 6 is also not significant, but there's a significant differences between the blocks. So you can see this has resulted into a reduction in the mean square for the residual. You have 0.1 compared to 0.2. So you've reduced the residual by half, by almost half. Now, what happens here is that although the variety is not significantly different, and when the variety is not significantly different, in this case, there is no need for you to go ahead and do the post-hoc test to use LSD. Now, if you go and use LSD, you may actually find that some varieties are different from each other, and that it will be due to what we call chance. Now, if you've heard of Fisher's protected LSD, means that when you only do LSD when there's a significant difference detected by the analysis of variance table. That's what called protected LSD. So you don't proceed to do LSD unless there is a significant difference detected in the analysis of variance table. So The same for 349 onward. It's just the simple running of the graph that we had before. So you can have them there. You can compare them. You can run them. So you can run them and try to explain them the way we did up there. I just want only here to go for the post-hoc test to show you why it's important to use Fisher's protected LSD. Because sometimes analysis of variance tells you there is no difference between what you're trying to compare, but if you insist and go ahead and do LSD tests, you might actually find significant differences. Let me go to the last. Okay, so we are going to run line 41, 411, and 412. So let's run line 411. So you can see from line 411, okay, for mode of 5, when you run line 4411, actually everything is A. So there's no significant difference between the varieties you're testing. But we should actually not even do the LSD test because we already know from the analysis of variance that the pairs are not significantly different. Let's run with adjustment. You don't expect any changes. But let's see what will happen when you run model 6. Okay, now see what will happen in model 6 now. Model 6 is now telling us that A is actually different from E and F. And remember, the analysis of variance table told us that the pair, they are not significant. Remember, analysis of variance, we fail to reject the H naught. When we fail to reject H naught, we're simply saying the means are all the same. But if you insist and go on and do your LSD, you actually find that there's significant differences. Now, this is where the correction factor becomes critical. Now, when you come and run line 415, you can see now because of the correction, everything is actually A. So here you can see that the correction is really, really very useful. Okay, so I think we have 6 minutes. I'm going to ask you to run the remaining part. So let me just explain what is remaining here. So we have an Irish data. So Irish data is one of the data sets that comes together with R. So please, you don't need to do anything. If you want to know what Irish data is all about, you run line 422. Then it gives you a description. Then you can run the rest of the lines without any problem. And this one, you can also see some beautiful, maybe you run and then explain. One person can demonstrate for us tomorrow. So let me just show you this picture, then we call it a day. Okay. So here we are looking at the sepal length versus the sepal width. But then here we colored it using the different species. So you can see the different species showing different colors. This is sepal length and sepal width. And then width length versus the length versus the width. So at this point, I'd like to hand you back to my boss to proceed from there. So Susan, you have your student with you. So thank you very much, everyone. So thank you very much, everyone.
I think it's me. Okay. Thank you very much, ladies and gentlemen. You've been so patient and excellent participants. We thank you so much. For tomorrow, we'll have day 3, and depending on what my colleague Dr. Thomas has covered, probably we will come in with the regression and correlation tomorrow. Okay, so I'll hand over to either David, Amitu, or Dr. Nyararo, or Selma, whoever is around, to close the session. Thank you so much, and we see you tomorrow.
Thank you very much, Prof. Maybe just a quick one before you hand over to us. There was a question that I saw in the chats asking if R is only for agriculture. Can you hear me?
Hear you.
You can, okay, there was a question in the chat that was asking if R is only for agriculture.
No, R is not only for agriculture. We can also use it for survey data. If there is time, Dr. Helen can demonstrate that using, when she's talking about survey sampling.
Okay, thank you. Thank you very much. Thank you very much, Prof. To you and the team. Thank you very much, Dr. Odong, for taking us throughout into the day 2 of this course and training, which is going on very well. We just want to thank the participant and also thank my colleagues who are online and are busy responding, putting up the links here and there. Thank you very much, colleagues. And we call it a day. Please, if you have missed anything, go and catch up on the YouTube channel so that tomorrow you come and be on the same page. Thank you and see you tomorrow.